Tutorial. We're going to do 4 things today. 4 things. The first is we're going to look in more detail, more quantitative detail, about the question of the spreading of the wave packet, specifically about the spreading of the Gaussian wave packet. This idea that these flying fuzzballs that are wave packets tend to spread as they grow older. Secondly, how do you come up with a relativistic theory of quantum mechanics? How do you marry relativity with quantum mechanics? The Schrödinger equation doesn't cut it. Can you come up with a different equation of quantum mechanics which is consistent with relativity? And then 2 discussion points. Here's 2 controversial statements by 2 famous physicists. The first, Asher Pears, one of the founders of quantum information science, says quantum mechanics needs no interpretation. We'll discuss this. And secondly, a quote from Stephen Hawking, who said equations are the boring part of mathematics. Now, since this is a physics course, if I just slightly misquote Newton and say that, Hawking, one of the successors of Newton, equations are the boring part of physics. This is something we can discuss. Do you agree with this as obviously true and why? Or do you disagree with this as obviously absurd and why? Now to the first thing, which is the Gaussian wave packet spread. So one of the things we developed in the last lecture was a horrible expression for the wave function associated with the so-called Gaussian wave packet. And by taking the magnitude squared of this object, we derived an only a slightly less horrible expression, or you derived, or will derive in exercise 39, a slightly less horrible looking expression for the probability density of this Gaussian wave packet. And it was a big equation. And as always, I'm unimpressed by big equations because I need to be able to look at them and see what's going on physically. So we want to be able to make this transition from the mathematics to understanding what underlies that mathematics. We had the spread of momenta, a point we explained in the last class. We call that delta px. We have this denominator which looks a bit strange. Delta px to the 4th, t squared, mass of the electron squared, h bar squared. And all of this multiplies something that has the form of a Gaussian. In other words, the exponential of negative something squared. Well, there's a negative. What's in the exponent? What's being squared? X, which is position. V, which is the average velocity of the particle. And then there's this huge multiplier at the front. Delta px on h cross squared. And a fairly ugly denominator. And they're showing that this probability density is derived from a wave function that obeys the Schrödinger equation is an exercise for you. But what I want to do now is to extract as much physical meaning as possible from our equations. So we're not deriving equations, we're understanding them. We're beating the path from a formula. Just because you can derive something doesn't mean you understand it. If you can't derive it, then you don't understand it. But if you can derive it, you don't necessarily understand it. We want to be able to extract as much physical meaning as possible. And for me, this is nothing more than a bunch of numbers, a bunch of constants, a bunch of functions. This means nothing to me. And I want it to mean something to me. So with a view to trying to work out what the hell this thing means, and with my usual mental blank coming on, what will this thing look like if I was to plot the probability density as a function of position x at time t equals 0 Can someone explain to me what this graph of the probability density will look like when t equals 0? Who'd like to begin?
Does it just look like a Gaussian?
Does it look like a Gaussian? Absolutely. It's going to be a Gaussian. What is a Gaussian, by the way, in its essence? What will be the
Bell curve.
bell curve? Beautiful. So Gaussian is a bell curve. The simplest Gaussian I could possibly write down would be e to the minus x squared. Now I could put some numbers out the front. I could put some numbers, a number multiplying the exponent. But the essence of the bell curve is e to the minus x squared. When t equals 0, this will just be some number. Because if t is fixed, everything else is a constant, that'll be some number. I don't care what it is, let me call it a. There you go. When t equals 0, and sorry I left a squared off here. When t equals 0, this is minus something times x squared, right? Minus something times x squared. And so this has the form of a number times e to the minus something x squared, the classic bell curve. Now, since this is a probability density, the area under this thing will be 1. Now I want this bell curve to grow old a little bit. I want to ask the question, instead of at time t equals 0, let me now ask the question at some later time. No, I don't have any system of units in time, so let me just call it t equals 1. This could be 1 second, 1 hour, 1 microsecond. I just want an indicative plot here. So the point is that t here is non-zero. Now this, let me now make a statement and ask you to justify it. Actually, better still, let me ask you a question. What is the value of a? A is the maximum value of this curve. A is the value that this curve has when x equals 0 and t equals 0. What will be an expression for a, the peak value of the curve at t equals 0? Yep, beautiful. So you're looking at this thing here. E to the minus something squared, right? That's all this line here is. E to the minus something squared. And the biggest that's going to be is 1. The maximum value this thing has is 1. Besides, when t equals 0 and x equals 0, this is e to the 0, which is 1. So this thing that's circled here is the peak value. And if we were to evaluate that at t equals 0, that's the peak value at t equals 0. It's just going to be what's circled with t set to 0. So there's the one on root pi that was mentioned. Delta p on h cross stays where it is. T is 0, so the denominator is the square root of 1. So this is it. This is the peak value. The value of a given here. So we can put that in. It's delta px on h cross root pi. Here's a physical question that I won't get us to answer, but I just want to make the point. Everything you write down has a physical meaning, everything, right? So we've just deduced that the peak value of this probability distribution, the peak value of this bell curve, is proportional to the spreading momenta. The bigger the spreading... In fact, let's interpret it now. Why is this peak value? Why is the height of this graph? I haven't asked myself this question before, but you've asked it, so let's go. Why is the height of this graph proportional to px? What does that mean physically? I'm trying to think of the answer myself. Yeah, go for it.
That means that as you get more sure of the position
Yeah.
of the wave packet, so the higher and more concentrated the area gets, then the more
Yep, beautiful. The more certain you are about the position, the more certain you are about the position, the more uncertain you are about the momentum. This is starting to sound a lot like the uncertainty principle. Yep. The bigger the peak value, the narrower it will be because the area must be 1. The bigger the peak value, the bigger the uncertainty in delta px. So if delta px is big, then this will be very, very high. But because the area is 1, it must be very narrow. And if it's very narrow, the width, and let me call the half width delta x, the width, the uncertainty in position, must be small. But this is exactly the uncertainty principle, right? The uncertainty principle says that the product of these things is greater than or equal to some number. So maybe there's the uncertainty principle built in here. Conversely, if the peak was very, very small in height, then delta px would be small, but the area had to be 1, so it had to be very wide and very fat. Again, this reciprocity, this idea of the spread in momentum and the spread in position being complementary variables. Fantastic. Now the question is to ask about the width of this object. How do I quantify, sorry, if we now let t become 1, the centre of the bell curve, where is the centre of the bell curve and why? And my hint is this. Where is the centre of the bell curve and why?
Is it at x minus vt?
Yeah, beautiful. The centre of the bell curve is where x minus vt equals 0. So if I was to have a bell curve that looked like this would be centred at x equals 0. If on the other hand I were to have a bell curve of this form, then it's going to be centred at the point where what I'm underlining vanishes, namely at x equals x0. Here x0 is vt, so the bell curve is going to be centred at the point of vt. Don't be fazed by the apparent complexity of what I'm circling in blue. That's just a number. That's just a number that depends on time. So this bell curve is centred at a particular position vt. The peak value is going to go down, right? Because as t gets bigger, what's circled up here gets smaller. So this peak value is going to reduce. The width is going to increase. We're actually going to write down an expression for this width. So I've indicated the width increasing. Gaussian moving to the right as it grows older, as t gets bigger, reducing in amplitude, increasing in width, becoming more and more delocalized. This is getting smaller, bigger, sorry, at the cost of, this is getting bigger and bigger. All right. I want an expression. Again, as we do so often, I want to flick from mathematics to physics, physics to mathematics, and to be able to do so fluently, I want an expression for the width of this Gaussian, of this bell curve. Now, when I ask the question, what is the width of a bell curve? That's actually an ambiguous question, right? Now, there's many ways to define width. So if I have a bell curve, and I want to work out what its width is, I'm going to work with the following definition. We have some peak value, A. Then we could go to some value which is 1 on E. E as in Euler's number. This is 1 on E times the peak value. Yeah. And by definition, this full width, or this width, defined as the distance between the points where the bell curve falls to 1 on E of its maximum value, this is going to be 2 delta x, right? So delta x is like a standard deviation. 2 delta x is a width. So I want to work out this, this delta x, and since the wave packet is fuzzing out, it's spreading with time, this delta x I would expect to be a function of time. And the question is, what is delta x as a function of time? How can we extract it by staring at equation 123? So we want to stare at this and pull out a delta x as a function of time. And again, I look at this equation and it's too big for its own good. Yep. Too many symbols. So can someone help me? I mean, I just want to change the notation, right? I'm not changing variables, I just want to change the notation. And I want the right-hand side to be as slim as possible, to be as compressed as possible. What should I call? I want a name. I want a name for what I've circled in green. What should I call it? A. Excellent. Actually, that's what I called it earlier. Good point. So this is A as a function of t. And as we've argued, this is the peak value. It's a function of t, so I've indicated that. In fact, A for amplitude, right? So this is the peak value of the wave packet. And then we have this thing here. And there's no right or wrong answer here, right? Do I want to just write this out, or do I want to give it a name? If the former, y, and if the latter, y, what would you like me to do with this expression? Both answers are right, it's just a question of choice. And if it's wrong, that's trial and error, that's fine. What should we do with this bit?
Can you relate that to A as well?
Sorry?
Can you relate that to A as well?
Can we relate this to A?
You just say it's
So this is A squared. Again, I didn't know this. Delta px on h cross gets squared. This gets squared. And then a 1 on root pi. Fantastic. I like that. So what's here is the same thing as there's an A of t squared. There's this x minus vt squared. And the root pi, is that on the top or on the bottom? On the bottom? Yep, excellent. So,
No, it's on the top.
it's on the top? Yep.
And it's just pi.
It's on the top and it's just pi because it's been squared. Excellent.
And you need a negative.
And I need a negative, thank you. Not doing very well. Anything else? Cool, thank you. So we have our bell curve. We already know that it's centred. This is for the probability density. We already know that it's centred. This is at a particular time t. We already know that it's centred at vt. This is the peak value A. I want to know what these positions are. These are special positions, particular positions which I'll call x tilde. At these particular positions, the probability is going to fall to 1 on e of its maximum value. Just to repeat, at these special positions by definition, the probability density will be 1 on e of its maximum value. This is going to help me work out what I mean by the width, because this width is going to be delta x as a function of t. What do I do next?
Substitution.
Substitution, excellent. I'm being thick. What do I substitute into what?
A on E for X.
Yep. So I need A on E for rho of x. So the probability density is going to be A on E, and that's going to equal A times e to the something, and that something is just what's in here. Now, I'm going to do the easy bit. So we've got e to the minus 1 equals what's in the square. Yep. So e to the minus 1 equals what's in the square. So therefore, what's in the square must be negative 1. This has to be negative 1. All right. That equals negative 1 means I can throw away the negative sign. I've got a pi. I've got an a squared. I've got an x minus vt squared, and that's going to equal 1. But this is for the special values, x tilde. What do I do next? Not a trick question. Even I can answer it.
Solve for x.
Solve for x. So to solve for x, I'm going to take the square root. So I'm going to divide through by this object here and take the square root. I've made a mistake. What is it?
Square root pi.
Absolutely. I've made a second mistake. What is it?
Got the plus or minus?
Forgot the plus or minus, superb. So this means that x, these special values of x, are going to equal vt plus or minus something. And that's fully consistent with this. It's vt plus something and vt minus something. So plus or minus 1 over root pi a of t. So the plus or minus, it's plus delta x or minus delta x. That this delta x is precisely what I'm circling. This is delta x. Yep, that is delta x. I'm actually not sure if what I just said is correct. Is it correct? Is what I've circled delta x? Because I'm working without notes here. That way you can see me think. All right, let's see if it works. We're going to get a formula and we're going to ask ourselves, do we believe it? Because the first 2 times I derive anything that I haven't derived before, I get it wrong. And then when it converges, when I derive it the same way 2 or 3 times, then I start throwing bullets at it and ask the question, do I believe what I've derived? So let's do this. And also, can we extract as much physics as possible? The width of the Gaussian wave packet as a function of time is 1 on the square root of pi, and we have a of t, and a of t is this. So this, so we have a of t equaling this, and a of t is on the denominator. Yep. A of t is 1 on the square root pi, which gets rid of this. Remember, a of t is on the bottom. We'll have delta px on h cross. All on the denominator. And we'll have this square root. And that square root will be on the numerator. Yep. So I stare at that formula. Is it correct, by the way?
Yes.
It is, excellent, thank you. So I think that I've got a formula. So this is the formula for the width of the Gaussian wave packet as a function of time. And now what I want to do is, like Jimi Hendrix extracting beautiful sounds from his guitar, I want to extract as much physics as possible from this. Okay, it's a bad analogy, but it's the best I can think of. So let's plot this thing, this width, as a function of time. Let me ask the question, what is the width at time t equals 0? Does someone want to shout out the answer? What is this at t equals 0? So h bar over delta px, so this value here is h bar over delta px, because when t equals 0, this is the square root of 1, the width is h bar on delta px. How about when t is infinitely big, what will delta x be? If t is infinitely big, then Even if the answer seems ridiculous, shout it out. What does the maths tell you? That if t is infinitely big, then delta x is as well. Excellent. So this thing is going to become infinitely big. I'm not quite sure yet how it's going to grow to infinity, but it's going to grow to infinity. It's going to head off to infinity. When t is minus infinity, this formula doesn't care about the sign of t. This thing's also going to increase to infinity when t is minus infinity. And at this stage we might be a bit confused, right? Because I was telling you about the spreading of the wave packet, right? This is the spreading of the wave packet. Its width is getting bigger as time increases. But now we're getting this idea that it also gets bigger if you go backwards in time. So let's trust the mathematics, right? Because this formula is correct and this curve is correct. Let's trust the mathematics. Physically, this is the spreading of the wave packet, right? And we had, I drew a movie where the wave packet started like this and then got broader and broader as it travelled to the right. T equals 0, t equals 1, t equals 2. Probability density versus position. And so this is the wave packet spreading as time grows older. What's this graph telling you about, because t can be negative, no problem. Origin of time is arbitrary. If t is negative, the wave packet also spreads as you go back into the past. So what did the wave packet look like? And the centre of mass is moving at constant speed to the right. According to Ehrenfest's theorem, Vt1, Vt2, etc. If you go backwards in time, the wave packet shrinks. Sorry, the wave packet spreads as you go backwards in time or forwards in time. So the wave packet gets thinner, it's at its thinnest at t equals 0, and then it expands. So I sort of lied when I said wave packets always spread, because sometimes wave packets collapse. But you know physically that sometimes things can contract and sometimes they can expand. Here we have an example of precisely that. Infinitely delocalized wave function collapses to some minimum width and then expands again. Now let me make a physical comment and then another mathematical one. The minimum width as we've already argued, is h cross on delta px. As you stare at this formula, what word or words or idea emerges into your head as you stare at this blue formula? Again, deliberately vague question, because I want you to make associative links. Uncertainty principle. So this looks a lot like the uncertainty principle, right? If we multiply through this delta px, you get the uncertainty in position, or in fact the minimum uncertainty in position, because now we have an object, a quantum object, whose uncertainty in position changes with time as a wave packet collapses and spreads, that's fine. But the minimum uncertainty multiplied by the spread in momentum, which is independent of time, equals h cross. So this looks a lot like Heisenberg uncertainty principle. The Heisenberg uncertainty principle, the HUP, looks a lot like this. It says that the uncertainty in position times the uncertainty in momentum is greater than or equal to h bar. Now sometimes there's a h bar on 2, it all depends on how you define widths. But for the way that we've defined widths here, this is a h bar. So I've drawn a suggestive squiggly blue line because I want you to compare this equal sign with this inequality. Again, what physics thoughts are provoked in your head when you look at this expression?
In the top one you've got delta x min is equal to?
Yes.
Whereas in the lower one it's the inequality.
Yeah, beautiful. So here we have a delta x min and here we have an inequality. At any other time, this delta x will be bigger than its minimum value, and at any other time, this right-hand side will be bigger than h bar. By the way, this is called an uncertainty product for two reasons. It appears in the uncertainty principle, and also it's a product of uncertainties. Yep, uncertainty product. It's also telling us that this is in some sense a very special wave function, because this is true for any wave function, but at least at one particular time, when delta x equals delta x min, for that particular special time, this is what I would call, or what Schrödinger called, a minimum uncertainty wave function. You have all these uncertainties in quantum mechanics. What is the closest that you can get to classical mechanics in a quantum setting? And one answer to that ultimately unanswerable question, but one answer is you're as classical as possible when your uncertainty is minimized, that at least for this particular time when delta x equals delta x min, this inequality, there's a lowest, there's a bound from below on this uncertainty product, it's h cross, but when you get these magic wave functions, or more precisely these minimum uncertainty wave functions, which minimize the uncertainty, in some sense they're as classical as possible. Now Schrödinger called these things minimum uncertainty wave packets. Glauber called them coherent states, which is actually the modern term. We've just learned that a Gaussian wave function is an example of a quantum system which has as little quantumness as possible in the sense of a state of minimum uncertainty product, even if it's only for one particular time, t equals naught. These coherent states are immensely important in the theory of modern quantum optics, boson-Einstein condensation, quantum chaos, quantum optics, general relativity, standard model of particle physics, quantum field theory, Large Hadron Collider, and so on. These things are very, very important. So important that Glauber, who systematically studied these so-called coherent states, 1963. If you want to find his papers, go to physicalreviewa.aps.org, which is the Physical Review, which is a famous physics journal. You'll be able to access this from within Monash. Look up Glauber, look up 1963, you'll find his Nobel Prize winning papers on coherent states. Gaussian wave packets are not the only states of minimum uncertainty product. What is the most general set of states with minimum uncertainty product? These things are called coherent states, and they're immensely important across theoretical physics. But I digress. So I've extracted some physical meaning regarding the uncertainty principle here. I want to now switch on some, what's it called? Maths brain. Yep, maths brain. So let's look at this again. We know what this thing looks like when t equals naught. We know what this thing looks like when t diverges. But now I'm going to ask the question, which is a little bit more refined from a mathematics perspective. How does this thing tend to naught? And how does this thing tend to infinity? Sorry? Delta p is power of 4, thank you. This delta p is a power of 4, thanks. How does this thing tend to naught? And how does this thing tend to infinity? Yep. So let's begin by how does this thing tend to infinity? More precisely, how does delta x approach infinity as t approaches infinity? So I want to ask the question, how does delta x tend to infinity? What is the asymptotic behaviour of x as t becomes large? Again, this squiggle just means tell me how the thing behaves when t is infinitely big or becomes arbitrarily large. Now, the question's vague, right? When I say large time, what do I mean? Do I mean, because if you talk to a high-energy particle physics physicist, they'll define 10 to the minus 22 of a second as a large time, because it's much longer than the time it takes light to travel the width of a quark, right? If you ask a cosmologist what a long time means, they won't say 10 to the minus 20 of a second, I guarantee you. The point is that when I say long time, that's too vague. What do I mean by large time here? I could just say t tends to infinity, but I want to be more precise. And the mathematics is going to tell us, staring at this formula, we're going to ask the question, what do we mean by large time? And
Greater than 1.
sorry?
Far greater than 1.
Far greater than 1, fantastic. We can render precise the idea of large time because this is going to be much larger than 1. Yep. So when we say much larger, time large, that's a vague, imprecise statement. When we say that what's circled is much greater than 1, that's good, I like that. That's precise. Delta px to the fourth, and again, thanks for picking that up because I would have screwed up the answer otherwise. T squared, m squared, h cross squared, much greater than 1. So we can raise this to the power of a quarter and solve for t, right? T has to be much, much greater than something. Square root of m, square root of h cross, divided by delta px. So this is what we mean by large time. You might also want to check that this is dimensionally correct, and I'll screw it up. Can someone tell me what I should have done?
Square root.
Square root, excellent. I want to get a t, so I need a square root. Because I said it's got to be dimensionally correct, and I looked at it and said it's not dimensionally correct. M h cross on delta px squared. Do we buy this? No complaints, that's cool. So this is what we mean by t being large. And when t is large, this is much bigger than 1, so you can ignore the 1, right? You can ignore the 1. So let's just scrub the 1. If t is large, delta tx will be roughly, or will tend towards h bar. We have a delta px. That 1's disappeared. So we get the square root of px to the fourth, which will be px squared, delta px squared. The t squared becomes a t. The square root of m squared becomes an m. The square root of h bar squared becomes h bar. And we can cancel. We always feel good when we cancel. And so you get that delta x of t is asymptotically equal to px t on m. So delta pxt, which by the way is linear in t. It's linear in t. So this tells me that this curve I've drawn is a little bit inaccurate. Here's a straight line, which I'll draw in blue. That is delta px t on m, it's proportional to t, and this is asymptoting towards this line. If we were to have t infinitely negative, you'd asymptote in the opposite direction. So this thing is asymptoting to a pair of straight lines, or a pair of crossed straight lines, plus or minus delta px on mt. How do I know this is dimensionally? If a formula is dimensionally correct, it may or may not be correct. If a formula is not dimensionally correct, it's definitely wrong. Can someone explain to me why this formula is dimensionally correct? As in the left-hand side has the same units as the right-hand side. And I'll begin. The left-hand side has the units of a distance. Hence, mental blank.
Kilogram meters per second.
Sorry?
Kilogram meters per second.
Kilogram meters per second.
Times second divided by kilograms.
Yep. So a momentum has the units of a mass times the velocity, which is kilograms meters per second. T has the units of a second, which will cancel s to the minus 1, and we divide by m, which has the units of kilograms, leaving meters, which is the units of distance. Excellent. So this is dimensionally correct. So we've just answered the question of how this width behaves for arbitrarily large t. Now I want to ask the opposite question. How does this behave for small t? And again, I just want to be a bit vague in what I write on the board. What happens when t is small? Now when t is naught, we know what happens. Now I want t to be small. What do I mean by t being small? As I stare at this formula here, t is small, then
The circle expression is much less than 1.
yeah, beautiful. The circled expression is going to be much less than 1. So circled expression is much less than 1. Delta px to the fourth, t squared, etc. Is going to be much less than 1. We can take the square root of this. A 4 becomes a 2 becomes a 1, the squares disappear. We pull the m h bar on the left-hand side, or we solve for t, right? And hence t must be much less than m h cross on delta px squared. So this is what we mean by small t. And now we ask the question, how does this formula behave when t is small? Now when it was 0, we just switched this off and said that it's a square root of 1. But I want to be more sophisticated than that. I want this thing that's circled to be small, but not 0. Yep. At this point in time, the binomial theorem, or the binomial approximation, sorry, comes to mind. We have 1 plus a small number, theta, small as in its magnitude is much less than 1, precisely what we have here. And if I raise it to some power a, then that's approximately equal to 1 plus a theta. It's as if the a is a frog that can hop in front of the theta. It's called the binomial approximation because these are the first 2 terms in an in general infinite series called the binomial series. So, if t is small in this sense of the term, then what does our expression look like? So I'm not sure what to write here yet. I just need to write this big formula again. The width h bar and delta px, we realise again that this is just the uncertainty principle. Something to the power of a half. That's the square root. I'm writing it in this form to make it look like this, because I want the half to be a frog, right? 1 plus something small, which is what I circled earlier. Now, I apply the binomial approximation. This is an approximately equal to sign. That half hops out the front of what's small, which is delta px to the fourth, etc. Good. This half is gone, right? It's hopped out the front. What do you see when you stare at this? Again, turn off your physics brains. As what do your mathematics brains tell you when you see this? What's the form of the equation? Is it an exponential? Is it a, sorry, parabola? Beautiful. This is a parabola. This is a quadratic in t. It's a constant plus something times t squared. It's a parabola. So if we look at our curve here, what we're doing is we're fitting a parabola to it. I'm sure that parabola is going to be wrong if t is large in magnitude, but for sufficiently small t, the parabola is a good approximation to the true curve, and that parabola is given by the boxed equation. So this is a parabolic approximation for small t. Now what I've tried to do is to extract everything that I possibly can from the formula for the width of the Gaussian wave packet. Right, I've tried to extract everything that I possibly can from this. How about something else that can be extracted from this? Some piece of physical meaning, some insight? Or am I pushing my luck? I genuinely can't think of anything else, by the way. That doesn't mean there isn't anything, but so I shouldn't have said that. What else can we get out of this? I'm sure you can think of something. There's a challenge for you. Look this up on, extract one more piece of knowledge from this, and then please post it to Moodle, and I'll be very impressed, and so will everyone else. Now, seriously, just because I can't think of it doesn't mean it doesn't exist. It just means I'm not being imaginative enough. Seriously. Let's actually skip the question of relativistic quantum mechanics. We'll do that in the next tute. 4 minutes isn't quite enough for that one. I want to look at these two quotes. So suppose someone says to you at a party, quantum mechanics is weird. Then you say, okay, lemon trees, quantum mechanics shouldn't be weird. But nevertheless, we're speaking the language of wave functions, operators, Schrodinger equations, uncertainty principles. All of these things are not directly intuitive. I can't think of a wave function or a wave packet in classical terms. It's not classical, it's quantum, it's weird. But I want to interpret it. Someone says I want to interpret it. I want to be able to think of it in classical terms. And then Asher Pears comes along and says, nah, you're fooling yourself. Don't bother asking what quantum mechanics means. It's not intuitive, bad luck. Quantum mechanics needs no interpretation. What do you think of that? Would someone like to agree with that statement and explain why? And would someone like to disagree with that statement and explain why? Who'd like to kick off for either side?
It's
Yep.
a pragmatic approach to maybe you don't have as much work to do.
Yep, so it's a pragmatic approach. Can you elaborate on that a bit? This is good.
If you don't need an interpretation, you don't have to come up with one.
Yep, you don't need an interpretation. You don't have to come up with one. Quantum mechanics predicts the results of measurements. What more do you want? Why do you want to interpret that? Go to the philosophy department. So this is a pragmatic approach. Does someone want to argue the opposite approach, that that's not good enough, to say quantum mechanics needs no interpretation? All I care about is the numbers. What more do you want?
It's not pragmatic if it limits your ability to further the theory.
It's not pragmatic if it limits your ability to further the theory. Beautiful. Can you elaborate on that?
If interpretation can illuminate a way forward to build on the foundations you've already established, then it is meaningful, beyond just helping us to understand it intuitively.
Yeah, beautiful. If the interpretation can illuminate the way forward, then you could ask questions about furthering quantum theory, but asking questions about interpretation can illuminate. Instead of saying needs no interpretation, you might say no, interpret it, you need to, and then that might well illuminate the way forward. Remember, by the way, that quantum mechanics as developed here was very much considered a provisional theory. When Schrodinger wrote down his Schrodinger equation, he never wanted or expected that to be anything more than provisional. He wanted to work out what the hell it meant to illuminate the way forward. Schrodinger was pissed off that he couldn't go any further than he did. And here's a quote from Schrodinger, and this is fair income. All this damned quantum jumping, I'm sorry that I ever had anything to do with it. So that's Schrodinger. Planck said something similar. Planck introduced the quantum hypothesis as a provisional thing. Planck was extremely pissed off that it stuck, right? Okay, you won a Nobel Prize for it, but he's still pissed off about it. Ditto for Schrodinger. They both had the view that was just mentioned. You need to interpret it because we don't understand what's going on. We don't understand what's going on because we can't picture it in classical terms. Understanding what the hell is going on at a deep level is the way that you illuminate the way forward to looking for better theories. So you've seen two different perspectives on this question. By the way, I hold a superposition of both perspectives in case you know or care. And you shouldn't care, right? You should think about what you think about this. Debate this with your mates. Debate this with me. Debate this on Moodle. Debate this on Facebook. Here's another one for you. Equations are the boring part of physics. Homework is to think about that. Thank you. Have a good weekend, and I'll see you soon.